Welcome to one of the most mind-bending demonstrations in quantum physics, Hardy's paradox. Imagine two particles, or two players, in separate rooms that somehow affect each other without any visible connection. This is the essence of quantum non-locality. Let's understand what makes Hardy's paradox such a powerful demonstration of quantum mechanics. Unlike Bell's theorem, which uses statistical inequalities, Hardy's paradox provides an all-or-nothing proof of quantum non-locality. It reveals correlations between measurements at distant locations that simply cannot exist in any classical theory. The beauty is that no classical local realistic theory can explain what we observe, making it a definitive proof of quantum weirdness. Picture two players in separate sealed rooms. What one player does affects what the other observes, but we cannot trace any causal connection between them. Let's start with a simple classical analogy to understand what makes quantum mechanics so strange. In our classical setup, imagine two separate rooms. Each room has a coin and a detector that can check two different properties. Room A has a detector with two settings. We can check if the coin is facing left or right. Room B has a detector with two settings. We can check if the coin is facing up or down. Here we see the two rooms. Room A checks left-right orientation, while Room B checks up-down orientation. In classical physics, the coin has definite properties before we measure. The results are predetermined by hidden variables. Now let's see how quantum mechanics changes this picture completely. In the quantum version, we replace coins with entangled quantum particles. These particles are fundamentally connected. This is the Hardy state. It's a special quantum entangled state written as a superposition of three terms with specific coefficients. The 1 over square root of 3 factor ensures the state is properly normalized, meaning probabilities add up to 1. The two particles A and B are entangled, connected by quantum correlations that have no classical counterpart. Each experimenter can choose between two different measurements, just like our classical setup. Alice in location A can choose to measure her particle in either the U basis or the W basis. Bob, in location B, can choose to measure his particle in either the V basis or the W basis. The W basis is a superposition state, defined as 1 over square root 2 times the sum of U and V states. Here are the measurement choices. Alice chooses between U and W, while Bob chooses between versus and W. Now comes the paradox. Let's see what quantum mechanics predicts for different measurement combinations. First prediction. If Alice measures in the U basis and gets outcome yes, then Bob will never get outcome yes when he measures in the versus basis. Mathematically, the probability of Bob getting V equals yes, given that Alice got U equals yes, is exactly 0. Second prediction. If Bob measures V and gets yes, then Alice will never get yes when she measures U. The probability of Alice getting U equals yes, given Bob got V equals yes, is also exactly 0. These first two predictions show perfect anti-correlation. When Alice gets yes for U, Bob must get no for V, and vice versa. Here's where things get truly bizarre. The third prediction contradicts classical logic. Third prediction. Sometimes, when both Alice and Bob choose to measure in the W basis, they both get yes results. The probability of both getting yes when both measure W is 1/12, or approximately 8.3%. This precise probability comes directly from the Hardy state wave function and quantum mechanical calculations. When both measure W, there's a small but definite probability that both get yes. This seems impossible given the first two predictions. Let's examine why these three predictions together create an impossible situation for classical physics. From prediction 1, if Alice gets U yes, then Bob's particle must have property V no, because the probability is 0. In classical thinking, this means Bob's particle had the property V equals no even before measurement. It's a predetermined fact. From prediction 2, by the same logic, Alice's particle should have the predetermined property U equals no. Classical logic forces us to conclude both particles have predetermined values, U equals no and V equals no. Now we reach the heart of the paradox. The classical conclusion contradicts observation. Here's the contradiction. If both U and V are no, then mathematically, the W measurement cannot give yes for both particles. Remember, W is a superposition of U and verses. If both U and V are in the no state, W cannot be yes. Yet quantum mechanics predicts that both getting W yes happens with probability 1/12, which we can verify experimentally. Classical logic says the probability should be 0, but experiments show it's 1/12. This is the paradox. We have a direct contradiction. Classical physics predicts probability 0, quantum mechanics predicts 1/12. You might wonder, can we save classical physics by introducing hidden variables? Let's explore this. Hidden variable theories propose that particles carry hidden information that predetermines all measurement outcomes. If such variables existed, they would restore determinism and local causality to quantum mechanics. Imagine the particle carries hidden variables, like a hidden instruction set that determines all future measurement results. But the answer is definitively no. Hardy's paradox proves that no local hidden variable theory can reproduce quantum predictions. Any local realistic theory must predict probability 0 for both W measurements giving yes, but nature gives 1/12. Let's look at actual experimental results that confirm Hardy's paradox. The first experimental verification was done by Lundin and colleagues in 2009 using entangled photons. They measured a probability of 0.082 plus or minus 0.003. The theoretical prediction is 1/12, which equals 0.0833 repeating. The experimental result agrees with quantum theory within experimental uncertainty, confirming the paradox is real. This graph shows the remarkable agreement between quantum mechanical prediction and experimental measurement. Let's make this more intuitive with a simpler analogy that captures the essence of the paradox. Picture two magic boxes in completely separate rooms with no communication between them. Each box has two buttons, one red and one blue, and displays either a happy face or sad face when pressed. Here are our two boxes. Each has a red button and a blue button. Rule 1. Whenever you press the red button on box A and get happy, box B's red button never shows happy. Rule 2. Whenever you press red on box B and get happy, box A's red button never shows happy. Rule 3. Sometimes, when you press both blue buttons, both boxes show happy faces at the same time. This seems logically impossible, yet quantum entanglement makes it real. This is Hardy's paradox in everyday language. A natural question arises. Does this mean information travels faster than light between the particles? The answer is no. This is one of the most common misconceptions about quantum entanglement. While the correlations are instantaneous, no usable information can be transmitted faster than light. Alice cannot control what result Bob gets. She cannot use this to send a message to Bob. No signal can travel faster than light. The correlations only become apparent when Alice and Bob later compare their results. Correlation does not equal causation or signaling. The correlations exist, but no signal passes between the particles. Hardy's paradox highlights the crucial and mysterious role of measurement in quantum mechanics. Before measurement, quantum particles don't have definite properties. They exist in a superposition of all possibilities. A quantum state is written as alpha times state 0 plus beta times state 1, a superposition of multiple states. When we measure, the system is forced to choose one definite outcome from the superposition. Before measurement, all possibilities coexist. After measurement, only one outcome remains. This is the collapse of the wave function. For entangled particles, this collapse happens instantaneously across both particles, no matter how far apart they are. Let's dive deeper into how we calculate that crucial 1/12 probability. Starting with the Hardy state, we need to transform it into the W basis to calculate probabilities. We express U in terms of W using U equals 1 over root 2 times W plus W dash bar. Similarly, V equals 1 over root 2 times W plus W bar. When we substitute these expressions and expand, we get the Hardy state written in the W basis. The probability of both W measurements giving yes is 1/3 from the Hardy state times 1/4 from the basis transformation, giving 1/12. This calculation shows how the 1/12 probability emerges from the quantum state structure. Let's compare Hardy's paradox to the more famous Bell's theorem to understand why Hardy's is so powerful. Bell's theorem establishes inequalities that any local realistic theory must satisfy, and quantum mechanics violates these. Bell's inequality involves correlations E that must satisfy this mathematical constraint in classical physics. But Hardy's paradox is all or nothing. It predicts an event that classical physics says is impossible, yet it happens. Hardy says the probability must be exactly zero classically, but quantum mechanics predicts a positive probability. Hardy's all-or-nothing nature makes it a more direct and arguably stronger demonstration of quantum non-locality. Hardy's paradox forces us to reconsider our most basic assumptions about the nature of reality. Locality is the intuitive idea that objects separated by space cannot instantly affect each other. Realism is the idea that physical objects have definite properties, whether we measure them or not. Hardy's paradox proves definitively that we must abandon at least one of these intuitive notions. We have to choose which to give up, locality or realism. The choice has profound implications for our understanding of the universe.